When a drug company is trying to determine whether their medicine works, a typical experiment that they'll run is they'll take one group of people, give them the medicine, they'll take another group of people, give them a placebo, which is a fake medicine, and then they'll measure something. Usually there'll be a difference. And the big question is this difference due to the fact that the medicine is actually working, or is this difference because of just regular randomness of the two groups? Because remember, these are two different groups of people, so you expect there to be a difference anyway. And so to help decide between those two situations, the main tool we're going to use is called probability, because probability is going to tell us how likely is this difference due to just pure regular randomness of the two groups. What is probability? Probability is a number that measures how likely something is to happen. In particular, it's a number between 0 and 1. And actually, we're more familiar with probability when it's as a percent. So when you go look up the weather, you'll see things like the chance of rain today is 60%. That 60% is a probability. So we can always convert these numbers here to percents. 0 converted to a percent is 0%. 1 converted to a percent is 100%. So probability is a number between 0 and 1 as a decimal, or 0%, 100% as percents. If something has a 0% chance of happening or probability 0 happening, that just means that it will for sure never happen. If you ask me, are you going to go skydive? I tell you, nope, 0%. That means that that's never going to happen. If something has a 100% chance of happening or probably 1 happening, that means that it will for sure happen or will always happen. If you ask me, are you going to go to the party this weekend? I say, yeah, I'll be there 100%. That means I will for sure be there. If you ask me, are you going to the gym today? 20%. So how do we actually compute probability? So before I tell you how to compute probability, let me introduce some terminology. Sample space. A sample space is a list of all the possible outcomes of a probability experiment. So what do I mean by probability experiment? I just mean any process where we don't know for sure what's going to happen. So for example, if I flip this coin, I don't know for sure what's going to happen. If I roll this dice, I don't know for sure what's going to happen. If I ask you, is it going to rain today? We don't know for sure what's going to happen today. So those are all probability experiments. So even though we don't know for sure what's going to happen, we can list out everything that could happen, and that's called a sample space. So in this example of this 12-sided dice, when I roll it, I don't know for sure what's going to show up, what's going to happen, but I can tell you everything that could happen. Okay, that's called a sample space. S for sample space. And we're just going to list out everything that could happen. So when I roll this dice, I could get a 1, I could get a 2, I could get a 3, and then all the way up to, this is a 12-sided dice, so the highest number I can get is a 12. Okay, and I'm just going to list all that out. I get a 1, a 2, 3, and that's the sample space for this 12-sided dice. In other words, everything that could happen when I roll this dice. 1 all the way up to 12. If I ask you, is it going to rain today? Okay. We don't know for sure what's going to happen today, but we can list out everything that could happen. It could rain, or it can not rain. Okay, we don't know for sure what's going to happen, but we do know that one of these things will happen. Either it rains or it not rain. So how do we actually compute probability? The equation I have here is a formula for what's called theoretical or classical probability. And it really only applies to a situation where the outcomes in the sample space are equally likely. Okay, and that's important for this formula. So in the dice example, if this is a fair dice, then each of these numbers here are equally likely to occur. Okay, that's what it means to be a fair dice. So this formula would apply to the dice situation. However, for the rain situation, rain, not rain, are these equally likely to occur? Especially here, California, when it's a drought, are these things equally likely to occur? No, right? Here, California, when it's a drought, actually not rain is more likely than rain. So these things are not equally likely to occur. So this formula would not apply to the rain situation. It would apply to the dice situation. So let's do an example with the dice situation. Say I'm playing a board game that involves this dice, and I need a number bigger than 7 to win. Okay, that's called an event. I'm going to call it E for event. An event that I'm interested here is bigger than 7. Okay, an event is really just a sub-collection of the sample space. And usually we describe it using words like this, bigger than 7. But in particular, what numbers are bigger than 7? Bigger than 7 would be 8, 9, 10, 11, 12, right? That's a sub-collection of the sample space. That's what an event is. But usually we describe it with words like this, bigger than 7. So how do we find the probability of getting something bigger than 7? Okay, so here's the formula. P of E, that just stands for probability of E, or probability of getting something bigger than 7, is, and it tells me here on the bottom, number of outcomes in the sample space. So we're just going to count how many things could happen in the sample space. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So counting how many things are in the sample space, just 12. And that's just a count of everything how many things could happen. On top, number of outcomes in the event E. So how many outcomes are bigger than 7? How many numbers are bigger than 7? So bigger than 7 will be 8, 9, 10, 11, 12. That's 1, 2, 3, 4, 5. There are 5 numbers bigger than 7. And that's the probability of rolling this dice and getting something bigger than 7. 5 over 12. That's as a fraction. We can always convert it to a decimal by just dividing. So 5 divided by 12. Okay, that gets us a decimal. And here it is 0.417. So that's rounded to 3 decimal places. And notice it is a number that is between 0 and 1. And then we can always convert it to a percent. So 0.417 as a percent, we would just move the decimal 2 to the right, and we'll get 41.7. Okay, so 0.417 decimal as a percent is 41.7%. So if I'm playing a board game that involves this dice, and I needed to get bigger than 7 to win, I have a 41.7% chance of winning. And I won. Sick. Example 1. A coin is tossed 4 times. Part A. Construct a sample space for this experiment. So when I toss a coin 4 times, I don't know for sure what's going to happen. So part A is asking for a sample space, which is just a list of everything that could happen when I toss 4 coins. So I'm going to think of this as 4 separate coins. So a penny, a nickel, a dime, and a quarter. Because I want to distinguish between heads, 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 tails as different from heads, heads, tails, heads. So in both of those situations, there's 3 heads, 1 tail, but I want to count those as separate outcomes. And the reason why I need that to be separate outcomes is because I want each outcome to be equally likely so that it satisfies the equally likely requirement for using this formula. So let's list out everything that could happen. I think the easiest way to list out everything is to organize everything is to just list it by how many heads there are. So when I toss these 4 coins, I could get 0 heads. And let's list out all the possible ways we can get 0 heads. Well, there's only one way, right? To get 0 heads, you would have to get all tails. So tails, 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 tails. And I think that's all. So next up will be 1 heads, or 1 head. And let's list out all possible ways you can get 1 head. Well, you can get 1 head by doing heads, tails, 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 right? What's another way you can get 1 heads? Tails, heads, tails, tails, right? So like I said, we're going to treat those as separate. What's another way I can get 1 heads? I can get tails, tails, heads, tails, and then what's another way? Tails, 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 heads. And notice all I'm doing is I'm moving the 1 head from the first position to the second slot to the third slot to the fourth slot. And I think that's all the possible ways you can get 1 heads. So moving on, 2 heads. This one's a little harder. So we're going to list out all possible ways we can get 2 heads. We can get heads, heads, tails, tails. And then we flip it. This will be tails, tails, heads, heads. Okay, that's another one. What else can happen? I can alternate them. Heads, tails, heads, tails. And then flip that. And that will be tails, heads, tails, heads. Is that all? Is there anything else? Is there other ways that we can get 2 heads here? We can have the 2 heads in the middle. And then flip that. That will be heads, tails, tails, heads. Putting the 2 heads on the outside. Is there any other way we can get 2 heads? I can't think of any, so let's move on. Next up will be 3 heads. What are all possible ways we can get 3 heads? Well, one way is heads, 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 tails. And notice here that 3 heads is the same thing as saying 1 tail, right? So this list should be similar to the 1 head list. So what we can do is just move the 1 tail from the last slot to the third, to the second, to the fourth. And that should get, or the first. And that should give us all the possible ways we can get 3 heads. Okay, so heads, 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 tails, heads, heads, tails, heads, heads, tails, heads, heads. And then moving the tails to the first slot would be tails, heads, heads, heads. And I think that's all the ways we can get 3 heads. And then 4 heads. What are all the possible ways we can get 4 heads? Well, there's only one way, which is all of them heads. And I did give a hint that there should be 16 outcomes total. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so I think we have them all. So once we have the list of everything that could happen, we can now answer some probability questions. Part B, what's the probability that there are exactly 3 heads? Okay, so to find probability, on the bottom is just a count of all the outcomes in our sample space. So here's our sample space. Count how many outcomes are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then for the top, how many outcomes have exactly 3 heads? So exactly 3 heads, that will be these right here, right? They have exactly 3 heads. So there are 1, 2, 3, 4. And that's the probability as a fraction. We can always convert this to a decimal by dividing 4 divided by 16. And that gets us 0.25. That's as a decimal. And then we can always convert that to a percent by moving the decimal 2 to the right. 2 to the right would be 25%. So on your lab, you can just enter the fraction. But you should know that you can always convert it to a decimal and then to a percent, which is what we're actually more familiar with. Part C, what's the probability that there are at least 2 heads? Okay, on the bottom, still the same, right? Total number of outcomes in our sample space. We said there were 16. Up top, we're going to count how many are at least 2 heads. Now, at least 2. What does at least 2 mean? Right? If I tell you you have to be at least 21 to purchase alcohol, what does that mean? At least 21 means 21 or over, right? 21 or more. So at least 2 means 2 or more. So how many of these outcomes have 2 or more heads? 2 or more would be all of these with 2 heads, these with 3, and these with 4. Okay, so all of those are 2 or more. So we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so there are 11 that have 2 or more heads. Part D. What's the probability that there are more than 2 heads? Okay, bottom will be the same, 16. For the top, we'll just count more than 2. So how many have more than 2? More than 2 means you don't include 2. So more than 2 would be the 3 heads and the 4 heads. So that's 1, 2, 3, 4, 5. Part E, what's the probability that there are at most 3 heads? Bottom will be 16. What does at most 3 mean? So at most 3 is similar to the at least 2, right? At least 2 means 2 or more. At most 3 means 3 or less. Okay, so pay attention to those keywords, at least and at most. You'll see those a lot in this unit. So for the top here, we're going to count how many outcomes have 3 or less heads. So 3 or less would be all the 3s, all the 2s, all the 1s, and all the 0s. Okay, so 3 or less would be 3, 2, 1s, and 0s. So all of those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Part F, what's the probability that the first and last tosses are the same? Bottom will be the same, the total number of outcomes in our sample space, which was 16. And then how many have the first and last toss the same? So first and last toss, the same. So either having tails, tails, first or last, or heads, heads. So that counts. It's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so those are, I count 8 where the first and last tosses are the same. Example 2. A 4-sided die and a 6-sided die are rolled. Here's a 4-sided, here's a 6-sided. When I roll these dice, I don't know for sure what's going to happen. Part A is asking for a sample space, which is just a list of everything that could happen. So whenever we have 2 dice, I think the easiest way to list everything that could happen is with a table. On one side of the table, I'm going to list everything that could happen on the 4-sided die. Okay, this is a 4-sided die. You could get 1, 2, 3, all the way up to 4. On the other side, I'm going to list everything that could happen on the 6-sided die. This is a 6-sided die, so you could get a 1, 2, 3, all the way up to a 6. And what I care about are the boxes on the inside of the table. So let me separate out these numbers up top and these numbers on the left side. So each box on the inside of the table represents something that could happen when I roll these 2 die. So for example, This box here represents getting a 3 on a 4-sided and a 2 on a 6-sided. This box right here represents getting a 2 on a 4-sided and a 4 on a 6-sided. Let's do one more. This box here represents getting a 1 on a 4-sided and a 6 on a 6-sided. So each box on the inside of the table represents something that could happen when I roll these 2 dice. Now let's take a look at these questions here. Part B, what's the probability that the sum is 5? The sum. Part C, what's the probability that the sum is greater than 7? Part D, what's the probability that the sum. All these questions are asking about the sum. So sum meaning adding them up. So this represents a situation that shows up a lot in board games where you roll 2 dice and you add them up. So because all these questions are asking about the sum, inside these boxes, I'm going to put the sum. This box here represents getting a 1 and a 1. The sum, or add them up, that will be a 2. This box represents getting a 1 and a 2. If I add those up, that's a 3. This box, 1 and a 3. Add them up, that's a 4. 1 and a 4, that's a 5. 1 and a 5, that is a 6. 1 and a 6, that's a 7. And then so on. So 2 and a 1, that's a 3. 4, 5. Okay, so once again, inside each box, I'm writing the sum. So this 8 here, I got that 8 because that's a 3 and a 5. If I add those up, it's 8. And I'm putting the sum because all these questions are asking about the sum. So these questions are asking about the sum, which is why I'm putting the sum inside those boxes. Now, we can answer the questions. Part B, what's the probability that the sum of the dice is 5? So probability, on the bottom, we're just going to write how many outcomes are in my sample space. The sample space here, remember, are the boxes on the inside. So how many boxes are on the inside of my table? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 24. A better way to do that is probably just go 1, 2, 3, 4, 5, 6, and then there are 1, 2, 3, 4 rows. So 6 times 4, 24. Up top, how many have a sum that is 5? The sums we wrote in red, so how many of them have a 5? 1, 2, 3, 4. And remember, we're only looking at the numbers on the inside, so don't count the numbers on the outside. 1, 2, 3, 4. We could convert this to a decimal and then a percent, but leave it as a fraction for the lab. Part C, what's the probability that the sum is greater than 7? Okay, the bottom, still the same, right? We're counting how many outcomes are in our sample space, which is represented by the boxes on the inside. How many boxes on the inside? We counted 24. How many of them have a sum greater than 7? So greater than 7 means bigger than 7. Bigger than 7 would be these 8s, these 9s, and these 10s. That's 1, 2, 3, 4, 5, 6. Part D, what's the probability that the sum is at most 3? Bottom, still the same. What does at most 3 mean? At most 3 means that the biggest it could be is 3. In other words, at most 3 means 3 or less. So how many boxes have a sum that is 3 or less? The sums, again, are the red numbers. So how many of them have red numbers that are 3 or less? So 3 or less would be the 3s and the 2s. That's 1, 2, 3. And then remember, we're not counting the numbers on the outside, so just the numbers on the inside of our table. Part E, what's the probability that the sum is at least 5? Bottom, still the same. At least 5. What does at least 5 mean? So this one's easy for me to remember because I just think of at least 21. You have to be at least 21 to buy alcohol. At least 21 means 21 or more. So at least 5 means 5 or more. So 5 or more. So how many of these have sums that are 5 or more? So 5 or more would be all the 5s, all the 6s, 7s, 8s, 9s, and 10s. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18. For F, what's the probability that the sum is less than 5? Bottom number is still the same, 24. Less than 5 would be the 4s, the 3s, and the 2s. So that's 1, 2, 3, 4, 5, 6. And again, remember, don't count the numbers on the outside. 1, 2, 3, 4, 5, 6. Example 3. 2 6-sided die are rolled. So here are 2 6-sided dice. When I roll these 2 dice, I don't know for sure what's going to happen. Part A is asking for a sample space, which is just a list of everything that could happen. So anytime I have 2 dice, the easiest way for me to list everything that could happen is to make a table. So on one side, I'm going to list everything that could happen on one of the dice. Let's do it for the blue one. So it's a 6-sided die. And this is for the blue one. 6-sided die, I get a 1 all the way up to a 6. On the other side, I'm going to list everything that could happen on the other dice, which is the red one. Six-sided die, I get a 1 all the way up to a 6. And again, what I care about are the boxes on the inside. So let me separate out these numbers that are on the top and on the left side. Since those numbers are just acting as labels here. So what I care about are the boxes on the inside. So each box on the inside represents something that could happen when I roll these 2 dice. So for example, this box here represents getting a 4 on the blue one and a 2 on the red one. This box here represents getting a 2 on the blue one and a 5 on the red one. And let's do one more here. This box represents getting a 2 on the blue one and a 3 on the red one. And now let's read these questions here. Part B. What's the probability that the larger number is 4? What's the probability that the larger number is less than 6? Notice that all these questions are asking about the larger number. So this is a situation that also shows up in a lot of board games where you roll 2 dice and then you take the bigger number. Or you roll dice and then you're allowed to roll again and then you're allowed to keep the higher number. So inside these boxes, I'm going to put the bigger number. This box represents getting a 1 and a 1. The bigger number would be 1. This box represents getting a 1 and a 2. The bigger number would be 2. This box, 1 and a 3. Bigger number will be 3. This box, 1 and a 4. Bigger number would be 4. 1 and a 5, that would be a 5. 1 and a 6, that would be a 6. 2 and a 1, bigger number will be 2. 2 and a 2 will be 2. 2 and a 3 will be a 3. 2 and a 4 will be a 4. 2 and a 5 will be a 5. 2 and a 6, bigger number will be 6, and so on. Okay, so once again, inside each box, I'm writing the larger number because these questions are asking about the larger number. Okay, so for example, this box here represents getting a 5 and a 4. The bigger number is 5. Now let's answer these questions. Part B, what's the probability that the bigger number is 4? So on the bottom, we're going to write how many outcomes we have in our sample space. Our sample space here is represented by the boxes on the inside. So how many boxes do we have on the inside? 1, 2, 3, 4, 5, 6. And then there are 1, 2, 3, 4, 5, 6 rows. 6 times 6, so that's 36. So there are 36 boxes on the inside. So you can count them one by one, or just there's 6 in each row, and there are 1, 2, 3, 4, 5, 6 rows. Up top, how many of them have a larger number that is 4? So the larger numbers are written in red here. So how many of them have a red number that's 4? 1, 2, 3, 4, 5, 6, 7. So again, don't count the numbers on the outside, just the numbers on the inside. So 1, 2, 3, 4, 5, 6, 7. Part C, what's the probability that the larger number is less than 6? Bottom number will be the same, okay, which is how many outcomes are in my sample space, which is represented by how many boxes are on the inside. And how many of them have a larger number less than 6? Less than 6 would be all the 5s, all the 4s, 3s, 2s, and 1s. That's a lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Part D, what's the probability that the larger number is at least 5? Bottom number is still the same. At least 5, what does at least 5 mean? At least 5 means 5 or more. So 5 or more would be all the 5s and all the 6s. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And again, only count the numbers on the inside of the table, not on the outside. Part E, what's the probability that the larger number is at most 3? Bottom number, still the same. At most means 3 or less. Okay, so get used to the terminology at least and at most. So at most 3 means 3 or less. 3 or less, so how many of them have a larger number that is 3 or less? In other words, how many of these have red numbers that are 3 or less? That will be all the 3s, all the 2s, and all the 1s. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Part F, what's the probability that the larger number is greater than 3? Bottom number is still the same, 36. Greater than 3 would be all the 4s, all the 5s, and all the 6s. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. In the examples that we talked about so far, we talked about flipping coins and rolling dice. Notice that in those examples, we didn't actually flip coins or roll dice. Right? We used what's called a sample space, which was a list of everything that could happen if we were to flip coins and roll dice. And then to find the probabilities, all we did was we counted from the sample space. So that's called the theoretical approach to finding probabilities. Another approach is called the experimental or empirical approach to probability. And in this approach, you actually are going to roll dice. So to find the probability in this situation, you actually do the experiment, like flipping the coin or rolling dice, and then you count how many times the event happens. On top, you just put how many times the event happens. On the bottom, how many times you did the experiment. So let me actually do one of our examples using the experimental probability approach. And the one I want to do is in our example 2, where we talked about the 4-sided and the 6-sided. And in that example, we talked about the sum, right? We rolled these two dice, and then we added them up. And what I want to talk about, the event I want to talk about is what we talked about in part C here, which was the probability of getting a sum that's bigger than 7. Okay, so let me actually write down the answer we got in that example. So we got a 6 over 24. So the event I want to talk about is sum that is greater than 7. And then from our example 2, our answer was 6 out of 24. And let me actually convert this to a decimal. 6 divided by 24 is 0.25. And remember, we got this using the theoretical approach, which means we didn't actually roll these two dice, right? We found a sample space, and then we got the top and bottom by counting. So now I want to do it using the experimental approach, which means I'm going to roll these two dice and keep track of how many times I get a sum that's bigger than 7. Okay? So here it goes. I'm actually going to roll this a lot. Okay, so 1 and a 2, that's a 3. 6 and a 2, that's an 8. So that's one time that's bigger than 7.
Three hours later.
Okay, so I got a little carried away. So I rolled the dice 5,814 times, and I got a sum greater than 7 1,483 times. So the experimental probability so how many times did I get a sum greater than 7? 1,483. And then how many times did I actually roll the dice? 5,814. I have no life. So let me divide this and actually get an answer. 1,483 divided by 5,814. Okay, round to 3 decimal places. This is 0.255. Now, I want to compare the two answers. This answer here, 0.25, we got this answer using the theoretical approach, which means we didn't actually roll the dice. .255, I got this answer by actually rolling the dice. This was the experimental approach. And notice that the answers they're different, but they're pretty close. Okay, so that's what this law of large numbers is saying, is that if you are doing an experiment a large number of times, the answer should be pretty close. And if you continue doing the experiment even more times, the experimental answer is going to get closer and closer to the theoretical answer. All right, that's a brief introduction to probability. Have a great day. See you next time.